Howdy, everyone. Happy April 7th. I looked on the internet to see if there was anything interesting that happened today, and I could find absolutely nothing. So this is one of those days of the year when nothing historical happened and I couldn't find any important birthdays. Now, the odds are that somebody in our class has a birthday today. So if you do, please send me a chat and we'll wish you a happy birthday. Someone says it's ring day for some people. So historical for some people. Okay. Somebody else asks why the wave expression there has a minus sign. It could be a plus or minus or even a multiplication or whatever we wanted, since it's not real true quantum mechanics. Okay, no volunteers for birthdays at this point. Turns out my brother has one tomorrow, but I'll settle for that. Okay, so we have started talking about statistical mechanics, which I think arguably might be the most important topic in the course for chemical engineers. But as we're seeing, this is dependent on understanding quantum mechanics also. We have to know where translational energy levels are, rotational energy levels, vibrational, and so on. So we started off last time just looking at putting balls into boxes and seeing what the weight of each distribution was. And we borrowed this equation from a statistics book. And this describes how many ways there are that you can do something. So we're putting some number of boxes, and we'll put N1 balls into box 1 and 2 balls into box 2 and 3 balls into box 3. Altogether, there will be capital N balls or molecules later, as we'll see. And then if we apply this equation, we can find how many ways something can occur. So here are the calculations. If we have all 3 balls go into one of the 2 boxes, there's only one way that we can do that. Oh, okay. Someone says April 7th is apparently the symbolic birthday of the internet. And what year would that have been? Does anybody know? It was already going fairly strong in the 1990s, so it's probably in the 1980s, I would guess. Okay, but let's stick to StatMech. So we see 3 zero works. We also saw trying to put 2 balls into one box and 1 in the second box. We come up with 3 different ways that you could do it. So we had our examples right here. So the first case was this right here. There's weight of 1. The second example, 2 balls in box 1, 1 and 2. There are 3 ways. And this formula works. And this is going to be very important for us as we try to figure out into which quantum states molecules go. The important point here is a particular configuration is more probable than others, or some are more probable. So you're much more likely to put 2 balls into one box. And if you look at the 2 possibilities, 2 into 1 or 2 into 2, that's 6 out of 8 possibilities would have 2 balls in one box. So in our example right here, we're only looking at 3 balls. So this is a very minimalistic example. When we get to molecular systems and we start looking at something like a mole of molecules, say 10 to the 23rd molecules, capital N is going to be very large and certain configurations are going to dominate others. Okay, somebody went back and they looked. Symbolic birth of the internet is April 7th, 1969. So it took quite a while for it to take hold. We started using it at A&M when I was in the dean's office in the early 1990s. So it took a while. Internet itself and emails. A lot of it was developed, I think it was called ARPA or something like that. It was developed for military purposes, the email system. And one of my good colleagues, who was a dean of science here at A&M, was actually involved in a lot of that system. Okay, so here's our picture of what we're going to be doing. First of all, realize that we can have all kinds of energies: translational, rotational, vibrational, electronic. All of them are quantum states. And any individual molecule has an energy which is a sum of those different kinds of energies. So in my diagram here, in my more or less horizontal lines, these represent possible quantum states that you can have. And they might be just translational or a combination of rotation and vibration. Doesn't matter, it's a quantum state existing in the system. So what we're going to do is we're going to take a fixed amount of energy from external sources, put it into the system. Basically, you can think of it as putting heat into the molecule. And now we're going to realize that that energy has to go into quantum states. It's just not arbitrarily going there and making something hot. It's going to be in individual quantum states. So we're going to take an E amount of energy, and we're going to have a capital N number of molecules. And each molecule is going to carry a certain amount of energy. When we add all of that energy up together, it's going to have to add up to capital E. So this is the model that we're going to look at. So these equations should be pretty obvious to you. The total number of molecules is going to be the sum of the populations of all the quantum states. So we're saying every particular quantum energy is going to have a certain number of molecules in that state. And it's typically going to be very large. I would guess at least 10 to the 18th, 10 to the 20th for many of these quantum states. But when we add all these populations together, it's going to be capital N, which may come out to be then something like Avogadro's number, or 10 to the 23rd. Total energy, this should be pretty obvious too, but it's slightly more subtle. Each quantum state is going to have an energy, E sub I, and it's going to have a certain number of molecules in it. So if you multiply the two together, that will be the contribution from that quantum state. So the subscript I here on their summation, this is what we're summing over. We're summing over the quantum states. We start at N1, then N2, then N3. The general state will identify as state N sub I, or a population N sub I at an energy E sub I. So this is a contribution from each quantum state, and we add them all together, we get the total energy. Now, we've talked a lot about 0-point energies, and we use quantum numbers V equal to 0 for vibrations and so on. Statisticians always like us to start at energy 0, or at the lowest value 0, and we're going to call that E sub 1. They don't like to do summation starting from 0, so we're going to say E sub 1 is 0. So that is going to mean that quantum state is not going to contribute anything to the overall energy that we have. But here's the picture again. We'll have N1 molecules in E1. That's the one with energy E0, N2 in E2, N3 in E3, and so on. So total number of molecules adds up. And then when we take this summation, that'll give us a contribution per state. And obviously, now there are going to be many, 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 many ways to distribute N molecules over the quantum states. And what we're going to figure out is what is the population of each quantum state going to be. We're going to get something called a partition function, from which we're going to be able to calculate entropies and enthalpies and things like that. So we'll understand where statistical mechanics comes from. I don't have a picture in my notes. Maybe I'll show it to you next time. But in your lecture notes, you'll find a description about Ludwig Boltzmann, who came up with statistical mechanics. And he came up with this even before it was understood that there were quantum states, and even before people really understood that there were atoms. And so he kind of had this model of entities, maybe not exactly atoms, but maybe they were atoms, going into different chambers or boxes, and they would have different energies. And he derived the whole mathematics of this without even realizing that there were going to be quantum states. Well, people didn't believe him, of course, because he was ahead of the game. And turns out, if I remember correctly, he went off in a lake and he committed suicide and drowned himself. But read about him in the lecture notes. Okay, so we're going to know the total energy, and we're not going to know exactly how the energy is distributed over all molecules. Some molecules are going to have more energy, others are going to have less, but they're going to add up so we have the same total energy. When we start looking at these distributions, we're going to want to find the most probable distribution that we have. And the most probable distribution is by finding which distribution has the maximum value of the weight. So if we go back to our box and use this formula right here, we saw the probabilities. This was 3, this was 1. But now when we go to larger systems, we want to maximize the W, because when you have 10 to the 23rd plus molecules, we can be quite sure we're going to have that most probable distribution for the molecules. If we miss it by a few million or billion molecules in a particular quantum state, it's not a big deal. It's going to still be a pretty good representation. So this is what we want to do, is we want the derivative of the weight to be 0. This is going to be dependent on the individual populations of the states. So we want to maximize the value of W. But when we do it, we also have to satisfy these conditions that I've been telling you about. Here I'm telling you again, notice that only excited states with energy other than 0 can contribute to the energy. So E0 does not contribute. The other thing I'm going to tell you right off the bat is we're actually not going to find the maximum of dW. If you think about the formula, and we start off with n factorial in the numerator, and capital N being 10 to the 23rds, 10 to the 23rd factorial gets to be a ridiculously humongous number that many of your calculators would be able to do. In fact, I encourage you, take your calculator and see what the highest factorial number you can calculate. I'll bet you can't get past 100. So now we're talking about 10 to the 23rd. Well, to alleviate this problem to some extent, what we're going to do is we're going to actually work with the log of W. So that'll be a lot smaller than W itself. And we're going to take the derivative of that and set it equal to 0 to maximize log of W. And of course, when we maximize the natural log of W, we will also have maximized what W is. Now, one more thing I want to tell you, this is what you learned in calculus. We're going to wind up writing d log W is equal to this summation. This is a summation over all of the quantum states. And what this is equal to, it says it's the partial of the log of W with respect to the population of that quantum state times the change in population of that state. And if you think back to your calculus, I'm sure you use this kind of equation a lot. If you want to know what the change in capital A is, you look to see how A varies with respect to X, and then you multiply it by how much X has changed. Then you look at the Y contribution and you look at the Z contribution. So this is just in maybe one system in three-dimensional space. Our problem is going to get immensely worse because we're no doubt going to have at least trillions of quantum states. So summation over I is probably going into the trillions. This is mostly thanks to the translations being very, very close together. If we want to talk only about rotations or vibrations, we may get by with only looking at dozens of levels for vibrations, or maybe only hundreds of levels for vibrations. Okay, so here's our summary, and I've put it in a nice big box here. And so this is the crux of statistical mechanics right here. So maybe 10 years from now, if you're working for Dow or DuPont or somebody, and they have you run a program to calculate statistical mechanics, this is what it most likely goes back to. I have a comment. Somebody said I thought e to the first was, e sub 1 was set to 0, not e0. Yeah, did I mistype something? We have no e0, so the first level is e1, and that's equal to 0. I don't know which comment we're talking about. Okay, so e1 is equal to 0. There is no e0. Okay, so again, focus on this box right here. So this is the total number of molecules. We added up all the populations of all the quantum states. This is the total energy. Each quantum state, I, contributes n sub I, e sub I energy. And the statistics formula we're going to use is this one that I've given you. Now I'm going to go a little bit further. I'm going to take derivatives, and I'm going to take dn of this. And so this will be, well, first of all, dn, capital Dn, has to be 0 because we're going to have a constant number of molecules. And so this is going to be equal to the summation of the changes of the populations of the states. So if I'm going to take 17 molecules out of quantum state 4, they're going to have to go somewhere, and maybe quantum states 3, 29, 28, and others will pick that up. So the total is still equal to 0. The other thing that we're going to have is that the total energy change is 0. We're going to look at an equilibrium situation with a constant energy. And so the derivative of this expression here is going to be e sub I times dn sub I. I'll point this out to you later. Well, in fact, it's right here. Notice that d e sub I is equal to 0, if you could make this out on the page. We know exactly where the quantum states are, so we don't have any derivatives that we can take from them. They're constant values. And so when you take the derivative of the two-term expression here, e sub I stays constant, and we take the derivative of dn sub I. Okay, for the weight, as I said, we wanted to maximize it. So in principle, we want d capital W equal to 0. We decided that works also if we just write the derivative of the log of W 0. And now we've seen, according to the chain rule, we can say this expression has to be equal to 0. And I have another chat comment. Okay, someone says there's an E0 at the top right of page 253. Okay, well, I won't go back to that, but for statistical purposes, we're not going to talk about an E0, so I might have had miswritten something. Okay, well, I'm going to tell you how all of this works together, but first I want to skip a couple of pages. And let's do a particular problem. And you're going to have a very similar problem to this in your problem set that you're assigned. And I personally like this very much because I think this is a beautiful way of understanding what's going on. We're going to get a little bit bigger than we had when we had 3 balls and 2 boxes. I'm going to take 5 different quantum states, and I'm going to have different energies for these quantum states as labeled. We'll say one quantum state has an energy 0, another delta, another 2 delta, another 4 delta, and a last one N5 at 12 delta. So this is not a harmonic oscillator or anything, but we need to come up with how these molecules are going to distribute. We're further going to say there are not only these 5 quantum states, but a fixed number of 6 molecules. And total energy we're going to put into the system has to be 12 delta. So my question is, figure out what are the possible distributions you can get for this system, and then calculate the weight for each distribution. So I've done that here. Typically, I very quickly get a question, how do you know what these distributions are? Well, it's basically trial and error. You just have to see what works for this arbitrary artificial system. The way I do this is I try to first occupy the highest levels as much as I can, and then I work my way down. So we have to get a total of 12 delta, and we have 6 molecules. So one way we can do this is let's put one molecule here up here at 12 delta. That takes care of all of the energy, and then we'll have 0 molecules in all the other quantum states except the lowest one, which has 0 energy. So 5 molecules will be in this lowest state. So according to the nomenclature that we have, and yeah, so N1, N2, N3, N4, N5, 5 in N1, the rest zeros, and 1 in N5. This would be the distribution that we have. And so for a 5 energy level system, this would be the formula we have to do. Capital N factorial, which will be 6 because we have 6 molecules, and then the factorials of all these individual populations. So quantum state 5 here with molecules N5, that'll be a 5 factorial. We have a bunch of 0 factorials, which you remember is 1 if you haven't run into that before. And 1 factorial, of course, is 1. So 6 factorial, of course, is 6 times 5 times 3, all the way down to 1. 5 factorial is the same, but it's missing the 6. And so this comes out to have a weight of 6. And I think you can all mentally figure out why there are 6 ways that you can do it. So I picked one of the 6 molecules to put into N5. Let's say that was molecule A. But I could also take molecule B and put it into N5. I could also put molecule C into N5. And there are 6 different molecules that could be that single molecule in N5. So there's 6 possible ways to get this distribution of the quantum states. All right, well, for all of these others, we're not going to try to figure out the weight logically, but we'll do the computation. Let's see how else we can satisfy this. If we put 3 molecules at energy 4 delta, that takes care of 12 delta. Then we put the other 3 at 0, and we have a satisfied situation. We have 6 factorial over 3 factorial and 3 factorial. And so this will come out to be the following, which comes out to be 20. So the likelihood of this distribution is about 3 times greater than this first one. And notice we're doing this by distributing the molecules over more and more quantum states as we do. Someone asks, why do we have an N6 in the factorial? That's because I mistakenly added it. 1, 2, 3, 4, 5. Yeah. You'll see I inserted a 0 here. I shouldn't have, and I inserted an N6 here. So I apologize for the mistake. There is no N6. There are only 5 levels, but the numbers still come out to be zeros because we have lots of 0 levels, and I'm just coming out that way. But thank you for pointing that out. Okay, so we're spreading more and more molecules into different states, and the weight goes up. Now let's reduce the number of molecules at 4 delta. So we get 8 delta out of here. And so we're going to need another 4 delta. We can get that by putting 2 into 2 delta. And so this would be our distribution. Bunch of 2 factorials in the denominator. This comes out to be weight 90. We go to 1 more. And you'll see we have 2, 1, 2, 1. This is about the broadest distribution of molecules we can have among those states. We still satisfy 12 delta, we still satisfy N6, and we get a weight of 180. I'm not going to go through these last two, but you can see in each case we'll come up with 12 delta, n equal to 6, and you can calculate what these weights are. So if you look at this picture, you'll see the 180 is 30 times more probable in occurring than getting all the energy out of just one quantum state. And now when we go to statistical mechanics, when we have 10 to a very, very large number, you can see that whatever high weight value we get, whenever we get the highest, this is going to be the distribution that we're going to have for the system. Okay, so as I said, you're going to have a practice problem like this or problem from your textbook. So work it out and think about it. But this is the heart of statistical mechanics. We want to use statistics to find out which one of these is going to be the most likely distribution. And even though this is a minimal explanation right here, just think about what happens when you go to a mole of molecules. Someone asks why it's not possible to put 6 atoms into 2 delta. Did I skip a level? That's quite possible. Yeah, that should have worked. So as I said, this is trial and error. When I'm going to give a problem like this, I'm sure, on your 3rd exam, and I will tell you specifically and have thought about it carefully. I'll tell you there are 4 possible distributions to figure out. But the main thing about this is just simply to see the effect of what the W term is doing in terms of maximizing population. Okay, somebody points out the page before there are 8 options and this only shows 6. So I did think it through, but obviously I ran out of room on this piece of paper. Anyway, think very hard about what we're doing here and think very hard about this, everything that's in the box. So this is what we want to do, is we want to maximize what dW is. In that page that I just showed you, we did this by trial and error. We saw that we could get that weight of 180 just by comparison. But let's look now to see how Boltzmann did it. And since we're a little bit short of time with lectures, I'll try not to belabor the math too much, but I do want you to be amazed by what he came up with. So quite possibly in chemical engineering, you run into the Lagrangian method. And the way that Boltzmann applied this, he basically said, d log W is equal to 0, dE is equal to 0, dN is equal to 0. So why don't we write an expression using all of these and just set it equal to 0? So this is the d log W term equal to 0. So that's the first term. And notice all of these are dependent on summations over all of the quantum states. So this comes from the d log W equal to 0. Then we see this term is equal to 0. Boltzmann didn't just add that term. He said, let's multiply it by an undetermined multiplier, which he called alpha. After we go through the mathematics that Boltzmann had, we're just going to throw alpha away. So it's never going to be anything of any significance, but it turns out to be useful in the derivation. And then finally, Boltzmann said, let's take minus beta times this term, which is equal to 0. So all of you can see, simply see, it's 0 plus alpha times 0 minus beta times 0. That obviously has to be 0. And so this is our expression now combined, putting everything under the summation sign. So we had this as individual summations, but we can put them all together, summing over the different quantum states. Now, without my trying to prove it, the statement that all the books tell you is the only way this is going to work is if this expression works for each individual state I, the quantum state with population n sub I and an energy E sub I. So I put a star next to this because we're going to be looking at this later. Okay, now I don't know if anybody as yet has tried to calculate the factorial of a large number. Seems to me I may have asked this class if you've seen the Stirling approximation before, but it turns out to be very important for statistical mechanics because we can use this formula to calculate what the log of x factorial is for a very large number. So in past classes, maybe you can report in next time, people can go home and compare how this expression works for the largest factorial that you can calculate, which I think is going to be less than a log of 100 factorial. But anyway, Stirling comes up with this expression here. And obviously this becomes a lot more manageable. We don't have to worry about taking individual factorials of numbers that are like 10 to the 23rd or something like that. Okay, so as I said, I don't want to belabor this, but we're just going to make this substitution then. So where we start off with log factorial being equal to this, Stirling then says, this is the result that we get. We get the log of the numerator. Well, no, this is just simple math. Any log can be broken down into the log of the numerator minus the log of the denominator. And sorry, some of this page didn't get scanned properly. I hope you have it in your notes. But this would be the summation of the these terms. So when you have the log or the product of many terms, you can write it as the summation of those individual expressions. So this would be log of n sub I factorial. Okay, then we apply Stirling. This is the substitution. And out of this substitution, we find that the summation over all the quantum states, which in this case we've converted to subscripts j, that's the value capital N. So it turns out we can write that the natural log of the weight is capital N log N minus this expression here. And this is now the summation again of the different quantum states. Hopefully it doesn't bother you that I'm switching from subscripts i's to j's, but I need to do that because later I'm going to wind up taking derivatives of n sub j's with respect to n sub i's, and I need to be able to have them possibly be different. And so in fact, I'll do that right here. So in our expression up here, you see we need the first derivative of the log of w. And so it comes out looking like this. Notice that the capital N log N term being a constant, this just goes to 0. So we can drop that out. So we're left with this expression. And as always, when you have two terms that you take a derivative of, you take the derivative of the first times the second, and then you take the first term times the derivative of the second. So that's the mathematics. So notice I have a star here, a double star there, and I'm going to be combining these down below in this page. Okay, so again, I don't want to speak lengthily about the mathematics, but I think you can all do this if you need to think about it. The derivatives dn sub j to dn sub I, all of them are going to come out to be 0 unless j and I are the same. This basically says the population of quantum state 24 does not depend at all on quantum state 35. And any state j does not depend on the population of state I. However, when the two subscripts are the same, we just have dni or dni, so that becomes 1. And so all of that just takes the derivative, this one, into this particular form. So again, this goes to 0 if j does not equal I, but it simply becomes 1 over n sub j for I equal to j. So we'll greatly reduce this messy term that we have up here. Okay, then we plug in here just simply what 1 over n sub j is, and it comes out looking like that. Now j has to be equal to I, so we simply just stick the i's back in here, and we get that this derivative is minus log n sub I plus 1. Now remember that n sub I is going to be incredibly large, 10 to the 23rd or larger if you're going to be dealing with barrels of oil, maybe 10 to the 26 or something. So even the natural log is going to be very much larger than 1. And what Boltzmann did then is, let's just approximate it by minus n log n sub I. There are some higher levels of statistical mechanics that try to keep that in there, but for the purposes of what we need mostly from statistical mechanics, we're just going to say this derivative term is just minus log of n sub I. We then go back to our expression star on this page. So we remember this is what we're starting with from each quantum state. We plug this back in, and so our first term becomes minus n log n sub I. Then we have plus alpha minus beta e sub I equal to 0. So we'll reorganize terms. I'll make log n sub I on the left be plus, and that way alpha can also be plus on the right-hand side, beta remains negative on the right-hand side. And I will now solve for n sub I star, defining that n sub I is the most probable distribution for that particular quantum state. So this is equal to e to the alpha minus beta e sub I. Well, at this stage, we don't know what alpha and beta are, so it's kind of puzzling. What are we going to make of this? But we can do the following. Each n sub I star is the most probable population of each state. And so if we add them all together, what we're going to get is the total population of the entire system in terms of e to the alpha minus beta e sub I. Whenever you have sums or subtractions in your denominator, you can split up the factorial. So this splits into e to the alpha, e to the minus beta e sub I. Alpha, you remember, is a constant. We can pull it out of the summation. And so this becomes e to the alpha summation over e to the minus beta e sub I. Okay, so notice what we have here. This is the population of one particular quantum state, and capital N is the population of all the states. So maybe we want to know what fraction of the molecules are in quantum state I. And so we'll take a ratio of n sub I star over capital N, and this is what comes out. And you'll notice the e sub alphas cancel out. And what we're left with then is this term right here, e to the minus beta e sub I in the numerator, and then the summation of the same kind of expression over all quantum states in the denominator. It turns out, as Boltzmann demonstrated, and I will show you later, beta comes out to be 1 over kT, K being the Boltzmann constant, T being the absolute temperature. And so when we substitute it in, this is the actual expression then that we have for the relative population of any particular quantum state. Out of curiosity, tell me in your chemical engineering classes whether you have run into partition functions before. I'm guessing even if you had, you probably had not seen the derivation of it, but let me know if you are familiar with partition functions. They have not, you have not, okay. Well, that's good, because I think this needs to be a very essential part of chemical engineering. again, when you're going to work with thermodynamics, you should be knowledgeable that most of the values that you use can be computed, and it's all based on statistical mechanics. All right, so this is a very important result. The details here in the math I went through just to show you that there's no black magic and you can go through it. But we come up with this result. And because we're going to run into this term in the denominator over and over and over again, and secondly, it turns out to be very important for being able to calculate internal energy. It's going to be useful for calculating entropy. We're going to give it a special definition. It's going to be called a molecular partition function. So it's the summation of the terms, the exponential to the minus e sub I over kt terms that we have. Okay, so just a side note, when I took my undergraduate course in physical chemistry, I unfortunately had a biochemist teach me statistical mechanics. I learned that there were partition functions. I had no idea where they came from. We were given formulas of what you could do with them. But I think it's really essential that you understand this background of where we started from. So this is where we start from. I think this is all common sense, except perhaps for the statistical formula that you can get out of a statistics book. And then we see that Boltzmann was clever by adding a bunch of zeros and working with the math and then coming up with a relative population of any particular quantum state. So always keep this in the back of your mind when we start working with partition functions. This is where it comes from. Okay, so we've done the practice problem. And at this stage, I just want to emphasize everything again, because I think this is the heart of understanding statistical mechanics. We have capital N molecules, and we have populations of each of these quantum states. The lowest energy state, E sub 1, has energy 0. It has a population N1. And then the higher states are going to have different energies. And our population total is going to be N1 plus N2 plus N3. And so I went up through N9, but typically we're going to be up into the jillions, whatever a jillion is. And then these quantum states, as I've indicated here, make sure you keep in mind, any individual quantum state is going to have a certain amount of translational energy. And if you're in the vapor phase, certain amount of rotational energy, certain amount of vibrational energy, certain amount of electronic energy. And then these are the contributions per energy to the total energy. Per state will contribute 0. In quantum state with energy E2, there will be N2 molecules. They will have an energy each E2. If you multiply that together, that's the contribution from that state. In the next quantum state, N3 molecules at energy E3 will contribute the product to that energy. You add all of that together, and that's total energy. Capital N is equal to this, as we see. Capital E is equal to that. dN is equal to 0. dE is equal to 0. And we've written these derivatives per each quantum state, and that way we could go and apply the Lagrangian method for coming up. So here it is. Here's the Lagrangian, here's our weight term. And so this is just a reminder of how you can split the log of W into log of n factorial minus the log of the denominator. Stirling approximation we need. Calculus tells us here is the chain rule we can do. And then this is the clever part. Again, 0 plus alpha times 0 minus beta times 0 is equal to 0. We come up with the most probable value. We divide by capital N. We get this. We later are going to find out beta is 1 over kt. And so Q, our partition function, here that in the denominator will wind up looking like that. So all of that is just the heart of statistical mechanics. Okay, what I want to show you next, and we have just a few minutes of time, the total energy is the sum of the contribution to the energy from each quantum state. So we have this expression. This is our most probable population of a particular state. And I'm now going to drop the star because we're going to assume that molecules are smart and they're going to distribute, well, let's just say they're Bayes statistics, and they're going to distribute according to the way that we get the maximum probabilities. We then can find that the most probable case is going to be n sub I is going to be equal to capital N multiplying through here, e to the minus beta E sub I over Q. The total energy, then, we can substitute into this expression here. Q, by the way, I didn't emphasize this enough, but it is a constant for a particular system at a particular temperature. So if you know what the quantum states are for a system, and you know the temperature, you can always calculate what Q is. So it's always from the e to the minus E sub I over KT summed over all the states. Okay, so I'm going to plug n sub I into this expression here. Capital N and Q come out in front. They're just independent of which quantum state we're looking at. Then we have the summation over all these terms. Okay, so just to show you where I'm trying to get to, I'm going to come up with a formula for the internal energy of a system based on the partition function. The internal energy that you would have probably had in chemical engineering, you probably called it U minus U naught, U naught being the energy at 0 degrees Kelvin. That's what capital E is going to be. Okay, so I'm going to take a derivative here of the exponential term, and you see that this comes out to be minus E sub I, e to the minus beta E sub I. And why I'm doing that is you'll see it exactly matches what I have in the summation here. So I can write that total energy as minus N over Q. The minus sign comes from here. And then the summation of the derivatives of d beta of the exponential term. And I can stick the derivative then in front of the entire summation. So all of these, we take the derivative. And so what the result is, since this is Q right here, it comes out to be minus N over Q dQ d beta. So the internal energy of any system is given by this quite simple formula. Now Q, as we're going to see, is not all that simple. We'll come up with some simple formulas, but in other cases, we'll have to do fancier calculations. When you go to work for Dow, they'll have computers that'll do those calculations for you. But you can very quickly calculate the internal energy of any system if you know what its quantum states are. And if you're working with something like benzene or ethylene or difluorobenzene, all those quantum mechanical parameters are known, and you can then calculate the thermodynamic properties. Now, the reason I was not very happy with my PChem course taught by a biochemist was he never really told us what Q was. And I can sort of forgive him for that because it doesn't really have an exact answer other than it's very useful for calculating things like internal energy. But despite that, books and I am going to try to give you a feeling for what the meaning of Q is. So here's a definition of Q. You have to start at the lowest energy level and you just keep summing them all the way up. If the temperature is 0, all of the molecules go into the lowest energy state, and we, by definition, say that E sub 1 is 0. And so we'll have e to the minus 0 over kt. E to the 0 is, of course, 1, and q is equal to 1. So all of the other terms then come out to be 0. if you go to t to infinity, which of course is the other extreme, Q just becomes infinite. All the quantum states are very heavily populated and you get a very large number. So trying to give you some sense of what's going on, this is a picture out of a textbook, and your book either has this one or one very similar. The volume, if you will, of the area shown for each quantum states indicates how many molecules there are. So if you're at low temperature, most of the molecules are going to be in your lowest quantum state. A few will trickle up into that first excited state. As you heat the system, you go to higher temperature, more and more molecules start going into other states. Further you go, you get more and more into upper states, and then you get to higher temperature. You get that a lot of the quantum states are occupied. Think back to our model of trying to put balls into boxes, or the case where I had n equal to 6 and E equal to 12 delta. You saw that the molecules want to distribute over as many states as possible. They don't want to just achieve all of the energy by filling in some upper levels. The lower levels, if you don't have degeneracies, are always going to be the most populated, and then the populations will trickle down according to this formula. Well, we've run out of time today, so we'll go on with that next time, and we'll see how we can calculate actually what some of these populations are, and we can see how we get further on getting some thermodynamic properties. But I very strongly encourage you to think about this picture right here. This is where it all comes from. And this picture is essentially exactly the same. In fact, this page, SMA-A, this is a summary of the heart of statistical mechanics. We've skipped a lot of the math that Boltzmann went through to come up with a result, but pretty much everything is right here. And someday, I think many of you will be using computer programs based on all of this. Just want to add a comment. When I first came to A&M, the chemistry department, or professor here, ran what was called the Thermodynamics Research Center. And then somewhere probably in the 1990s, it got transferred over to chemical engineering. And I haven't even checked if it exists anymore. But this organization was always highly dependent on knowing what vibrational frequencies are, because those are quantum states that have to go into your computation. So I would typically get at least 2 or 3 phone calls a week. Please tell us what you think the vibrational frequency is for dichloroethylene or something like that, if nobody had determined it experimentally. My answer always would be, well, we don't know unless we look at the spectra and try to do some force constant calculations. Today, we have computer programs that can calculate the structures of molecules very accurately. So it's very easy to get what rotational constants and structures are of molecules, which are needed for these computations. And the same thing with vibrational frequencies. The computations might not do it perfectly, but they will be doing it well enough that the thermodynamic properties can be calculated out correct to at least 1% or so. Experimental data is always better than theory, but a lot of times you need numbers at 500 degrees or 1,000 degrees centigrade, and you don't really want to have to do laboratory experiments to find out what the thermodynamic properties are of your dichlorobenzene at those temperatures. So stat mech is really very important, and very important for chemical engineers. Okay, so we'll go on with this Friday, and have a good rest of the week. A couple of chat questions. Okay, somebody asked why we assume the lower state to be energy 0, that's for statistical purposes. We can't have any molecules, well, how should we put it? We don't have any choice about 0-point energy. So 0 is defined as the lowest possible energy that we have in the system. Okay, it shows me how out of date I am. Thermodynamics Research Center moved to Boulder in year 2000. I guess I should have known that. I did a half semester sabbatical at University of Colorado Boulder, but I had in 2002, in fact, I think, but I didn't realize it had moved there. But thank you for that information.